Okay, last time we looked at Euler's method to solve a differential equation. Today we're going to look at solving a differential equation in a more efficient manner using a method called improved Euler's method. So let's say we have a curve here, and this is my curve f, and I'm starting here at the initial value t naught, y naught. I want to figure out some other value y sub n of this. What do we do? So with Euler's method, what we did was we would actually find the slope of that tangent line, and we'd go up a fixed delta t. So now we're here at delta t at a t1 right here, and that's y1. And then so we have this point here, and then we'd find the equation of this tangent line, or the slope of the tangent line right here, and so we'd find this slope here, and we'd go up another delta t. So from this point we go up another delta t, and we get to this point here. So let's say that's t2, and now we're at y2, and so on. We keep moving on. So as you see, we're kind of moving away from the curve. There's an error between where we are and what it should be. So improved Euler's does one extra step here. What it does, it says, okay, I have these 2 points here, y1 and y2. What I'm going to do is I'm going to take the average of these two slopes, actually. So I'm going to take the average of these two slopes. So that slope is going to kind of look like, and I'm going to draw it from this point where I started. So that average will look more like that here. That slope would be more like that. And then I find the equation of that line and step up a delta t right to here. And you can see a much more accurate prediction of what y1 would be if we did that. And we keep doing that. So then this becomes my new y0, and I go up with a tangent line and I find another y1, and then I go with a tangent line and find another y1, but then so I average these two slopes here, and the average of these two slopes would be something like that, and then I get my new t. I'll put that in a different color here. My new y, I mean. So we keep doing that, and you have a tendency to hug the curve when you do that with improved Euler's. So it's a more accurate method, and what we do is we'll have a t0 and t1 and a y0, but this y1 I'm going to call that a u1, and this will be a u2, this y value, because we're going to backtrack with these slopes to get this point here, which is y1. So let's see how we do this in Excel. Alright, so here we are with an Excel sheet. Last time we had used the differential equation dy dt equals t plus y. We had an initial value of y of 0 is 1, and we were looking for y of 1 using a delta t of 0.1. So here we have tn, the initial value of t, 0, and then un. So un would be yn in my normal Euler's. So t0, y0 is 0 and 1, and f of tn we use our differential equation, so that's equal to this one plus this one, right, t plus n. So that gives me my slope right there. Tn plus 1 is equal to now Tn. So Tn plus 1 is equal to Tn plus delta t. So here we have to fix this delta t by using a dollar symbol in between the letter and number. That fixes a reference. So that's my new t value. And the reason I'm doing that now, because we're going to use this again for another slope. But in the original Euler's we found un plus 1, so that was equal to my un, or my yn at that time, plus f of tn yn times my delta t, which is 0.1. So again, I want to fix that reference to delta t here. So that's so in Euler's, in the original Euler's, we would be using this number. This would be my new value to go back and do the whole iteration again. That would be the number we were looking for. But in our improved Euler's, that's not what we're looking for. So I'm going to unhighlight it. So what we're looking for is actually the new slope. So this slope is equal to t, which is now this t, plus y, which is that new y. So that's the new slope. So my first slope was 1. My second slope is 1.2. Notice I'm not looking for a u value. I actually want to average my slope. So two things you may want to highlight is this one here and this one here. Well, we're going to average those to find the slope we want to use. And so that's equal to, the slope we want to use is equal to the average of these two. So this one plus this one divided by 2. And that's the slope we want. So now we want to find y sub n using Euler's method, and y sub n, or y1, is equal to my y naught, which was u naught as well, plus this slope times my step size, and the step size is that 0.1. And I fix that reference. So my prediction for y1 is 1.11. Now, when we go back here, my t sub n really is, my new t is actually this t from here, because that we are going up by 0.1. So back here we could go equal to this tn plus 1 here. And my u1, we're going to use that as my previous yn. So this is going to be equal to, or my previous y1, this one here. And really the rest of this could be just brought down, copied and brought down like that. And once you take one row like that, you could bring down the entire thing. We needed 10 steps to get to y1, and we're looking for this number, so I'm going to delete all of this here. And so we see our prediction here now is quite different. Our prediction is 428162. 428162, and remember the actual was 3.4366. So that was the actual. So the percent error is about 0.2%. So 0.2% error using improved Euler's method, a far improvement over the 7.25% error, just with a few more calculations, and the same delta t of 0.1.